All right, the last lesson in chapter 9, 9, 10, we come back to looking at Taylor and Maclaurin series. All right, just to wrap up 9, 9, operations with power series. So if we have two different power series defined, then look at what we can do with these. We can multiply all the x's by some value. If I'm going to do that, then that changes the constant in the series itself. If I take x and I raise it to some power, if I think about replacing x in the series, then I have my power to a power. I can add known series together, okay? And you can also multiply and divide them. That's what we're going to look at today. The interval of convergence is the intersection of the individual intervals of convergence. All right, so if we have something like this, add these two series together. This is geometric ratio of x, first term is 1, so it converges on the interval from -1 to 1. Geometric ratio is x over 5, so that converges on the interval from -5 to 5. So the sum of the series will have an interval of convergence from -1 to 1, okay, the intersection of the two. Now, how can I write this as a single series? I'm going to I'll take the terms, add each individual series together. Then we notice here, I can factor that x to the n out. And what would that be? Leave me with 1 plus 1 over 5 to the n. Okay? With an interval of convergence from -1 to 1. So just simply, that's what the series would look like. All right, find a power series centered at 0 for the natural log of x squared plus 1. And I'm going to find this series by integrating the series 2x over x squared plus 1. Okay, so the series, not what I meant to do. So the series for 1 over 1 plus x squared, that would be 1 over 1 minus negative x squared. So that's my geometric, the first term of 1 and a ratio of negative x squared. Okay, so now I have n is equal to 0, -1 to the n, x to the 2n. Okay, so that's just manipulating our geometric power series. Okay, so now if I want 2x times that series, so now I have 2x times the series, 0 to infinity, -1 to the n, x to the 2n. Okay, well then let me multiply it through. So it would become the sum from 0 to infinity, -1 to the n times 2. Now when I multiply my x's here, this would become x to the 2n plus 1. So now this is the series for 2x divided by x squared plus 1. And now I have to integrate it to find the series for the original function here, the natural log function. Okay, so the antiderivative c plus my series from 0 to infinity, -1 to the n times 2, adding 1 to the exponent. So 2n plus 1 would give me 2n plus 2, dividing by the new exponent there. All right, so now I want to find f of 0. Okay, so plugging 0 in, I get the natural log of 1, which is 0. And then each term of my power series, they would all approach 0 as well. So I know c is equal to 0. Furthermore, I'm going to factor out a 2 from the denominator. And now I can get those 2 to cancel from the series. So the power series for natural log of x squared plus 1 would be the series from 0 to infinity, -1 to the n, x to the 2n plus 2, all divided by n plus 1. remember that we take the interval of convergence of the original. Okay, so here's the original series. Interval of convergence of this is from -1 to 1. So for homework, I want you to find the interval of convergence now for its antiderivative. So check the endpoints at x is equal to -1 and x is equal to 1. Okay, don't write these things down. So recall, now we're saying if we have a power series, then our coefficient, this should not be new to us. That's how we found the coefficient in a Taylor or Maclaurin series. So just redefines them. Okay, we know Taylor series are centered at C, Maclaurin series are centered at 0. Don't write these either. I'm going to hand out a sheet for this. These elementary functions, the series for these functions, you should be able to recall or recognize easily because we're going to start to manipulate them for other values of x. Okay, we've done, this is ln of x centered at 1. We've looked at all of these. We looked at them when we started with, I think it was 9-7 was the Taylor and Maclaurin series, and we went through the derivatives, we plugged in the centers, we found the values, but now notice you are given the nth term, okay? So these are very important, and again, I'll give you a handout of all this. Arc sine, I mean, really, we don't look at these two as much. We would look at arctan more so than arc sine or your binomial. Okay, so how is this useful? Find the Maclaurin series for the function sine of x squared. Okay, Maclaurin, center is at 0. Okay, so from our basic list of functions, the series for the sine of x is defined as 0 to infinity of this -1 to the n, x to the 2n plus 1, all divided by 2n plus 1 factorial. All right, so if I want the series for the sine of x squared, then all I need to do in the original definition what am I going to replace my x with? I'm going to replace my x with x squared. What this does is saves you the very time-consuming method of finding each derivative. Okay, if we found the first 3 derivatives, plugging in those centers, finding the value of the derivative, putting it over n factorial. We already know what the series is defined as, so we can manipulate that as needed. So now, -1 to the n, power to a power, this would be x to the 4n plus 2, all over 2n plus 1 factorial. Now sine and cosine both converge on the real number line, so the interval of convergence would be all real numbers. Now, how do the terms of the series help us? If I say, you know what, we'll do an example of that. All right, find the power series for cosine of square root of x. All right, so I know that the series for the cosine of x is defined as -1 to the n, x to the 2n, all divided by 2n factorial. And I'm sure you're thinking, do I have to memorize this? Not necessarily. All right, your elementary functions, your sine and cosine, that would be easy enough to find the Maclaurin series by finding the derivatives, plugging the derivatives in, but you got to make sure you recall that the coefficient comes from the nth derivative at c divided by n factorial. Then you could easily be able to determine what the nth term is. So a series for the cosine of the square root of x. So into our series. We replace x with the square root of x. Now when I look to this, okay, what's the square root of x to the 2n? Well, the square root of x squared will just become x. So I have n is equal to 0 to infinity. And this would just be x to the n divided by 2n factorial. The same interval of convergence of the real number line, negative infinity to infinity. Okay, last example, find the first three non-zero terms of the Maclaurin series for e to the x times arctan of x. So this is where the first terms, or knowing what the terms of the series are, will help us. I'm not looking for the power series itself. I don't need what the nth term is. What do I know? I know that the first few terms of e to the x are 1 plus x squared plus 2 plus x cubed over 3. Keep going. I know the first terms of arctan of x are x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7. Okay, so now I literally need to multiply these series together. And I have to maintain that we know it's infinite, but don't let this get you upset. I'm going to multiply everything by 1. So x minus x cubed over 3 plus x to the 5th over 5. Okay, I'm not going to go any further, and you're going to see why. Next, I'm going to multiply everything by x. So plus x squared minus x to the 4th over 3 plus x to the 6th over 5. Okay, so now remember what the goal is. The goal is to find the first three non-zero terms. So I have an x squared, and I have an x cubed. Now let me go one more multiplication, because when I take this x squared over 2 times x, it's going to give me a degree 3 when I find the product. So if I'm only looking for the first three non-zero terms, I don't need any of these. I just have to make sure that the multiplication gets me the proper exponents. So now when I put these together, the first three non-zero terms would be x plus x squared, and now let's do a little negative x cubed over 3 plus x cubed over half. So negative 1/3 plus a half, that would give me 1/6. So plus 1/6 x cubed. So that's my answer. All right, so complete the one endpoint test for the interval of convergence for me, and I'll see you in class.